When you figure out the electron configurations of the transition metals, what people usually do is they start at the nearest noble gas. And since we're looking at the first group of them right there, we will start with argon. Now, the first electrons to get filled in are the 4s electrons. So that would be potassium and calcium. But then right after that starts the first scandium, which is the first transition metal. That would be 3d1. Now, notice in that diagram, it's listed not argon 4s2 3d1, but argon 3d1 4s2. And there's a reason for that. We'll talk about it. If you were to write for me argon 4s2 3d1, that's fine. If you're to write for me argon 3d1 4s2, that's fine too, after you see what we're going to do with it here. So either way is cool. Titanium has one more d electron, so that would be argon 3d2 4s2. Vanadium would be argon 3d3 4s2. Chromium is an exception. We talked about exceptions to N plus L rule. So instead of being 3d4 4s2, one of the 4s electrons jumps ship and it becomes a 3d5 4s1. This is an exception to the N plus L rule. They do exist. If you told me the answer for chromium was argon 3d4 4s2, I'd be fine with it. But in reality, it makes an exception to the N plus L rule. That's what we're seeing. But then after manganese, it goes back for a while. So manganese, iron, and nickel all follow the same kind of patterns you can see. I skipped cobalt there because I was running out of room. However, when you get to copper, we see another exception. Copper should be at argon 3d9 4s2. One of the 4s electrons again jumps ship and goes argon 3d10 4s1. Again, copper and chromium are exceptions to the N plus L rule. Our rule for the figuring out electron configurations is not quite right. But then zinc fills in all of them. Argon 3d10 4s2, good to go. Neutral cobalt, if we wanted to figure out the electron configuration for it, first of all, I would definitely grab a periodic table. mhchem.org/pertab is the way to get the periodic table. That's what I would do. For neutral cobalt, first of all, look on the periodic table where it is. It's number 27, all right? And so number 27, if you go to argon, which is number 18, the 19 and 20 of potassium and calcium, that's the 4s2. And then literally starting with scandium, you can just count the number of d electrons. So scandium would be 3d1, titanium 3d2, vanadium 3d3, chromium 4, molybdenum 5, iron 6, and you can probably see then that cobalt is 3d7. So the answer for this one would be argon 3d7 4s2. And that's how I would figure this answer out. You literally just count over left to right. All I want you to know is the expected N plus L rule. You don't need to know the exceptions, so you can ignore those. Should be pretty chill. And again, if you wrote this as argon 4s2 3d7, I'm totally fine with that. We'll talk about why I'm writing it the other way in this section in just a little bit. This is another table that just shows how the different charges can really stack up. And again, most of these have more than one charge. Zinc is usually positive 2. That's one of the stairs, but the other ones definitely have more than one. So you can see how there's a variety of different charges, like manganese has a whole bunch of them. Now, one interesting thing that we're going to talk about a little bit, when you're making a charge on a transition metal, the highest N electrons come out first. And so in all of these transition metals we just saw, they were argon 4s2 3d something. Well, 4 and 4s comes out before the 3 of 3d. So you lose the ns electrons first, then you start losing the 3d electrons. This is something we talked about back in Chem 221 as well. Highest n electrons come out first, then the other ones come out after. So for these, it's really important. The 4 of 4s is higher than the 3 of 3d. 4s electrons out first, then you start taking away the 3d electrons. So back to the cobalt system. This time we have cobalt 3+, and we want to know how many d electrons this has. Now earlier we saw that cobalt was argon 4s2 3d7, all right? That's neutral cobalt. Now, cobalt 3+ means take away 3 electrons. highest N electrons come out before lowest N. So again, this is so sloppy, I can't write on the iPad with anything, but 4 of 4s is what I tried to write there. 4s to 3d7. 4 of 4s will come out before the 3d. So if you're going to take away 3 electrons, which is what 3 plus represents, the first 2 electrons come from here. Those 4s electrons are gone. But there's one more electron to take out because we need to take 3 electrons total, and that's going to come from the 7. So that means there's only going to be 6 electrons. So here's a little bit better representation of all this. Neutral cobalt, as we saw, argon 4s to 3d7. If you're going to take away 3 electrons, the first 2 will come out of the higher end, the 4s electrons. So both of the 4s electrons are out first. Then, if you have any more to take out, then you can take them out of 3d. So since we're taking away 3 electrons, we'll take them first out of 4s2. We'll then lower the 7 down to 6. Argon 3d6 would be the electron configuration for cobalt 3+. And hopefully now you can see why we're writing them as argon 4s2 3d7 or argon 3d7 4s2. If you're filling in electrons, it makes sense to write the 4s first and the 3d second. And honestly, that's what we've done up to this chapter most of the time. But if you're taking away electrons, it makes sense to write 4s last because they're the first ones to go. They weren't the last ones in, but they are the first ones to take out. So if you wrote cobalt as 3d7 4s2, the 4s electrons are out first, then you take away one of the 7s to make it 3d6, good to go. Anyway, either way you write it is fine, and they both have their utility. This is just highlighting again how you take away electrons. So iron, neutral iron, is an argon 3d6 4s2. It's one element to the left of cobalt, so it has one less d electron. Anyway, iron plus 2 is pretty readily made. That takes away 2 electrons. And again, the highest electrons come out first. The 4 is higher than 3, so the 4s electrons are out. Iron 2 plus, argon 3d6. On the other hand, iron plus 3 is also really common. So if you take another electron away, now it's going to come out of the 3d set. So iron 3 plus has a 3d5 in it right there. No problem. So for transition metals, actually all things, you want to take highest N first and then N minus 1, the highest one after that. So for transition metals, this group, that would be 4s first and then 3d. If it was the next group down of transition metals, like molybdenum, for example, then it would be 5s out first and 4d after that. So you can kind of see how this works, but it's important to realize those s electrons are the first ones out. Then we'll start working on the d's and be good to go. When you're making transition metal ions, you need to think about electron configurations and how they play around. And even the neutral atoms, it's kind of cool to think about what they are. So in Chem 221, we wrote 3Ds and 4Ss and filled them up with up and down arrows. And that's what we're kind of revisit here. So we talked about earlier how neutral chromium has an argon 3D5 4S1 configuration, which is pretty crazy. So 3Ds have 5 orbitals, 5 boxes, and you can see right there, there's 1, 2, 3, 4, 5. And it doesn't matter if it's 3D, 4D, 5D, 10D, all of the Ds have 5 boxes. We also talked about how the S's are just a single orbital, so that would be a single box. And even though it's not shown here, the p orbitals, there's 3 boxes, stuff like that. Hopefully this is kind of becoming familiar. Anyway, when you're placing electrons inside, you want to have individual electrons by themselves first and only pair up if there are no more places to go. So for chromium, which was 4s1 3d5, every box gets a single electron, and that makes paramagnetic chromium very paramagnetic because there are 6 unpaired electrons. Chromium is incredibly strong when it comes to attraction or sometimes repulsion to magnetic fields because you have so many unpaired electrons. On the other hand, palladium, which is further down, both of the s electrons jump ship, and you end up with a 4d10 configuration. And so when you figure out the electron configuration for palladium, every up electron has a down. So you can see that 4d10, every room is taken up. There's an up and a down in every box. There are no unpaired electrons by themselves. So this is diamagnetic. Diamagnetic things usually aren't as attracted or repulsed by magnetic fields as paramagnetic things are. Paramagnetic things tend to be more reactive, definitely. So chromium is very paramagnetic. It has 6 unpaired electrons, while palladium is completely diamagnetic. No interest in magnetic fields.